Welcome back. This is segment 2 of section 3.4. As you recall, I was getting ready to start into a couple of sort of applications and things that are pretty common in textbooks. So let me just shoot right over here and get working on them. So first off, I want to talk a little bit about the Earth, because the Earth tends to be something that is used fairly frequently in one of these situations because, well, quite simply, you know how fast the Earth goes around, more or less. I mean, I wouldn't say it's completely perfect, but there is some issues with. I think there's a problem in the textbook that gets students all the time because it's kind of a little confusing. So for a second here, I'm gonna look at the Earth from sort of a side view. Okay, so here's the North Pole, South Pole, and then maybe over here we can look at it from sort of a top down. So here's the North Pole, say. Okay, so hopefully everybody knows that the Earth rotates in this direction. It doesn't really matter the direction, but and its rotation is one complete revolution every day. So if we were to find its angular speed, the angular speed of the Earth is pretty easy. That's going to be, well, it goes through 2 pi radians. So this is like theta. In one day, which happens, if you want it in a different unit, is pi over 12 radians per hour. Sometimes that's a more appropriate unit. If you start getting into minutes and seconds and everything else, that's maybe like, I think these are really the 2 that get used. So let's talk a second about some features of the Earth. Now, hopefully you know that positions on the Earth are determined by latitude and longitude. Now, longitude, lines of longitude, all they basically start at one of the poles and go straight down the Earth to the other pole and then back up. So you end up with these like series of sort of like orange peel sections, and I'm sure you've seen that before. But latitude, if we look back at the Earth that's seen in profile, here's kind of where the equator is. And if you're at some point either north or south of the equator, this is given some kind of a designation, and the symbol that's often used for latitude in most geodetic texts is this V. So we'll call that latitude. And the one that's used for longitude is usually a lowercase lambda. And we won't really, at this point, we won't focus on longitude, but latitude is really the key here. Now, it turns out that the way that people measure these positions is kind of strange, because rather than going in one particular direction all the way around, or you get some situations where it's like north or south, east or west of a particular position. So if this is the North Pole in this picture, then this position on the Earth is at some longitude, which doesn't really matter, but some latitude that is north of the equator, right? So let's say that one way you might write that is, well, it looks close to a 45-degree angle, but I don't want to confuse it. Let's say it's 42 degrees north latitude. Now, what that says is that this angle, from looking at it from in profile, this angle, this acute angle in here, is 42 degrees. Now, if on the other hand, we were down in the southern hemisphere, this angle looks like maybe, oh, I don't know, maybe like a 62 or 68, who knows, 68 degrees south. So it's kind of, as I said, it's kind of a weird coordinate system, because if you were to ask what is the angle between these two, you'd add them up, right? So south latitude is like what you might call negative angles because it's counterclockwise rotation, or sorry, clockwise rotation from the equator. And north longitude is actually positive angles in the sense that we think about them in a trigonometry sense. But regardless, it doesn't make a whole lot of difference for the purposes of these problems. What I want you to recognize is that if we're looking top down, and this point, which is say at 42 degrees north latitude, might correspond to a point that's say right about there. And maybe the 68 degrees south latitude might correspond to a point that's maybe right here as we're looking from top down. So notice that the radius of rotation is bigger or smaller, right? It's maximal at the equator where the latitude is actually 0. And as you move towards the poles, it actually becomes 0. So there is a problem that's in the textbook that talks about figuring out the angular speed of a point, or not the angular speed, but the linear speed of a point at a specific latitude. Now, how would you find this individual radius? Well, look back at this picture, right? Back at this picture, this right here, this little branch is the radius. And for this point that's below it, this is the radius. And recall from our discussion about the unit circle, that's going to be in some way related to the cosine of the angle. Now, the only difference is this isn't a unit circle. This is a circle of definite radius, which is usually quite large. In the case of the Earth, it's like 6,400 kilometers. Well, how do we find this length? Well, that length is just going to simply be the radius of the sphere times the cosine of that angle. And that's sort of the part that people have a hard time adapting to for whatever reason. So let's do an example. Find the linear speed of Longview campus. Now, I will tell you from my experiences as a surveyor that the Longview campus is more or less at like somewhere between 38 and 39 degrees north latitude. 39 degrees north latitude is almost right on top of Strother Road. So to not make this too crazy, I'll just say we're at 39 degrees north latitude. So 39 degrees north. Given the Earth has a radius of 6,400 kilometers. Now, we're probably going to want to do this in kilometers per hour because that seems like a reasonable number to use. So let's say in km per hour. Okay, so going back to our, and I'll just say this, once you have access to those formulas we developed last time, the key to every one of these problems is in fact finding the angular speed right off the bat. And so, you know, people will, it seems like they confuse themselves by trying to find this other sort of stuff, but pretty much find the angular speed of these things and then work with those more simplified formulas. So recall that the linear velocity is going to be equal to r omega. Now be careful because this is not the radius of the Earth, okay? The radius of the Earth is actually going to be larger than the radius at which Longview campus is rotating about the pole. And it's going to be different by a value of cosine. So this is, to bust this out, we've got this as the radius of the Earth times the cosine of the latitude And because cosine is an even function, we haven't talked about even yet. They're both positive in quadrant 1 and 4. It doesn't really matter whether that's north or south. You could plug it, if it's south, you could plug in a negative, but you end up with the same thing. And then omega, which we determined up here in the right units, is pi over 12. And that's radians per hour. So that we'll end up with units of kilometers per hour, okay? And this is an application problem. Notice that none of these things have more than 2 significant digits. This is pretty exact. It's not, this has a lot more significant digits than these two, and so it's not really going to play any role. But if I just do the calculation here, I've got 6,400 times the cosine of 39 degrees times pi divided by 12, and I end up with 446 point blah blah blah. So this is telling us that the linear speed at this particular point, seems a little bit. I'm gonna run that calculation again, just so that I feel like I didn't fat finger or something. So 6,400 times 39 degrees, take the cosine of that, times pi divided by 12. Okay, so we've got 446.764, whatever. Now we want to apply only 2 significant digits. This only has 2, this has 2, this has more than 2, really probably. It's not a definite, I mean, the Earth doesn't exactly go around once every 24 hours. That's a fiction. It varies from day to day, but it's really, really small. So there's our 2 significant digits. So when we round this thing, we should round it to 450 kilometers per hour. And again, this is one of these situations where people feel nervous about rounding this. And it's like, well, you just follow the rules. I mean, just because it's pretty close to halfway does not mean anything. It's only good to 2 digits. So there's our 2 digits. Okay, so let me also introduce another kind of problem that pops up from time to time, and that one is ones involving clocks and clocks rotating. So we've discussed clocks before, at least in passing, and I wanted to spend a little bit more time on it. So depending on which hand we're talking about, so let's say on a clock, find omega for second hand, minute hand, and hour hand. Now, and I'm gonna say let's do it in radians per second for all of them. Okay, so first off, I want you to think about a second hand. How long does it take for the second hand to go all the way around? Well, it's not 1 second, and that's where you get tricked sometimes, because the second hand takes a full minute to go all the way around a clock, right? So in essence, it takes 60 seconds. So well, that's going to be how the omega is theta divided by t. The angular rotation is 2 pi radians, and the time it takes is 60 seconds. So the angular speed of the second hand is pi over 30 radians per second. Okay. And if you needed to do it in radians per minute, well, that's exactly 2 pi radians per minute. You know, you can do all these kinds of conversions once you have this. What about the minute hand? Well, again, the minute hand takes a full hour to go around, right? It takes a full hour to go around. So that's not that's actually 3,600 seconds. So it goes a full rotation, which is 2 pi radians, in an hour, which is 3,600 seconds, which this results in a value of pi over 1,800 radians per second, which is maybe not the most comfortable unit. It would be pi over 30 radians per minute, or 2 pi radians per hour. I mean, you can do all those kinds of conversions. Now let's finally think about the hour hand. The hour hand on a typical American clock, not a 24-hour clock, takes 12 hours to make a single rotation. And so the angular displacement, 2 pi radians, the amount of time it takes to do that is 12 hours. And then I'll convert from hours to seconds. So the unit I want to get into divided by the unit I want to get out of. And I'm just starting to get to big numbers. 12 times 3,600. Okay, so this is going to, when it reduces, you end up with this as pi over 21600 radians per second. Okay, so now if you wanted to, and like I said, I'll just go ahead and convert them to minutes as well. So sort of A2, because minutes might actually be more useful. So we would have 2 pi radians per minute. B2 is going to be pi over 30 radians per minute. And let's see, 2,600 times 60. So this is pi over 360 radians per minute. Okay, so that's pretty much all the combinations of the different types of hands. So here's kind of the problem. That's sort of some work that we do at the beginning, just to kind of understand, you know, sort of an approach to this. So if we have a situation where, what am I on, page 5, where we have a statement like this. The minute hand on a clock is 4.15 inches long. How far does the tip of the minute hand travel between, let's just give it a time, how about 2:45 a.m. and 1:30 p.m. on the same day? Well, maybe I'll, in order to bring this into line with a problem from this section, maybe also say, what is its linear speed? So this kind of combines some stuff from previous sections as well. So again, anytime you've got something about a clock, it is my recommendation that you simply determine the angular speed right off the bat. And in this particular case, it's going to be inches, maybe per second. It's not really specified. Let me just say inches per second, so that we do have a specified unit. So here's how we would start this. First off, we want to determine what the angular speed of the minute hand is in the right kind of unit. We just did that a minute ago. So recall that omega is equal to pi over 1800 radians per second. Okay. Now, the question is, if you want to find the distance traveled, right, that would be, remember, the omega is theta over t, but s, which would be the distance, is r omega, or r theta. So if you could develop this sort of extra equation that would say s is equal to r omega t. Right, that's just combining these two results, because you want to get theta out of it. Theta is equal to omega t, s is r theta, so s is r omega t. Right, this is actually theta here. So let's just start writing some things down then. So s is equal to 4.15 inches times the omega we found, which is pi over 1800. And then how many seconds? Well, this is kind of a lot of seconds. So first off, recognize that this 1:30 p.m. is actually the 13th hour of the day. So 13:30, if you want to think of it in a 24-hour clock. So the difference in time between these two is what? So we've got 10 hours and 45 minutes. Let me just make sure, because if I add back 2:45 to this, I'll get to 13:30, which is what I wanted. Okay. Now, the problem is this is kind of written in a weird way, because it's, and then 0 seconds. So we got to figure out how to turn that. That's in hours right now. Notice that this is 10.75 hours. So maybe I'll just do a quick conversion here. Sorry, 0.75 hours, and then convert to seconds, which is actually, going to end up with some cancellation here. We could probably reduce this to 4.15 and then 2 pi. Might even make sense to move. I mean, now we're in a different unit. Okay, so the question might be how many significant digits we have here. So let's see, 4.15 times 2 times pi times 10.75. So it looks like 280 some inches. And for our purposes, we have 3 significant digits on the distance. We have 4 significant digits on the time. Remember, this is just a conversion, so that's exact. So we need 3 digits on the result, which gives us a value of 280 inches. And I put that little dot there to represent that the 0 is a significant digit. Okay, so just to finish this off, I'm going to maybe quickly complete the velocity question about this. So 6. I know my video is getting a little long here, but this is really all I wanted to cover. Okay, so the relevant, now that we have some of these other bits, the relevant equation, you could use any one of these combinations, right? But remember that V is just R omega, right? We don't, sorry, R omega. And that's pretty trivial because that's just simply going to be 4.15 inches times, and because it's the units we want to be in, pi over 1800 radians per second. Okay. And again, we'll have 3 significant digits here, but if we just punch this out, times pi divided by 1800, looks like kind of a small number, but that makes sense. I mean, the minute hand isn't really booking around the surf, around the loop, and it's not a very long arm. So this is 0.007243116 and some stuff. And again, this will have 3 significant digits. So we're going to round this to, and I might just put this into scientific notation. So 7.24 times 10 to the minus third inches per second. Now there's all kinds of other ways that you could manipulate this, but I know there's a clock problem, maybe even 2 of them in the homework. And I usually will put one on the exam where it's something along these lines. So just like I said, from the very beginning, with any of these rotating spheres or circles or things like that, the first thing to do is to determine the angular speed in the right unit. And then you use these formulas, which are, relatively intuitive, to try to find, either you're given certain pieces of information, you try to find others. Okay, so I think that's probably good for section 3.4. We will see you again soon.